So back in single variable calculus, you were saying you had a constraint and you had an objective function. So my objective function is going to be my volume. So just for visualization. So let's say we have the blocks X, Y, and Z. That's a volume. And it says without a lid. So my volume of this box is going to be equal to V, Y, B is equal to X, Y, Z, right? The multiplication of it. And now my constraint is corresponding to this is the surface area of everything. Now our surface area without the lid, that's the key thing, is going to equal to this. And there's only one of them because there's only the box bottom right, no lid out at all. And we know if I plug this just into 12, this is what we get. Now, just like single variable calculus, right, we want it in terms of either one variable or two variables when it comes to our objective function, right? That's the reason why we have our constraint. Now, in our case, we've always had two variables, right? X and Y, because we're doing minimums and maximums. So in other words, we want to get rid of a Z because that's the problem. So using our objective function, we're going to solve for Z. So if you notice, we have Z right here and there. So subtracting this and then dividing all that bad boy out, we get this. And now, if you plug this in for Z here, we get our volume to be a worse mess than it was beginning with, right? Like that. Now this problem now becomes far more complicated because, well, first off, we have to do is in order to get to the minimum maximums, we have to find the partial derivatives now with respect to X and Y and set them equal to 0. Now, if you notice, this is the worst part, right? So if you want, I can distribute this to make it a little easier to look at. But there's no way around. We have to use the quotient rule, everybody's favorite, right? So just in case you guys forgot quotient rule, quick little reminder. It has lots of F's and G's everywhere. Okay. So the quotient rule is easier if you remember is derivative of the bottom times the top minus derivative of the top times the bottom. That's another way alternative are just using F's everywhere itself. Okay. However, it's very particular on the order because we have the subtraction, so just be careful. You first start with the derivative of the top times F. So in this case, this is going to be our F, this is going to be our G. When it comes to or low D high, that's another way I heard it. So that's another one, it's like high D low minus D high times low. But it's all over G squared at the bottom. Okay. All right, so we're going to do this twice. Okay, so for the first part, I won't go into the mere basics, right? So it's just partial derivative with respect to X. So for example, the derivative of G would just be 2. So it'll be 2 times all of that minus derivative of this with respect to X will be just 12y minus 2x y squared all over this and all over that squared. So I'm just going to skip that initial step and just give you what the answer is going to be just for the sake of time. X is a 4. Oh no, you cancel. That's a 2. Yeah, that's right. It's a cancel. It's still a 2. Yeah. Okay. And now if I do the same thing for by, the good news is they're almost identically the same. So same process now, just partial derivative with respect to y. So again, this is just going to be 2. This is now going to be 2 times all of this on top, minus derivative of this partial with y will just be 12x minus same thing, y squared x squared times this, all over that squared. And it's very interesting. They're almost identical. Now, before you say, well, wait, no, wait, this is going to be horrible. It's actually not that bad because remember, we're setting them equal to 0. So if we set this equal to 0, notice if I just factor, or just rewrite it for you guys. Okay, here we go. So if we set that equal to 0, we want to solve for one variable, right? Meaning I have to multiply both sides by this part. Well, if I multiply both sides by on the bottom, notice 0 times that just goes away. So really, I just have this happening. And same thing on this side. Here. So the interesting part is, well, according to factors, right? So if I factor in set equals 0, therefore each factor set to equal to 0. Now notice y cannot be 0 because that doesn't make sense, right? That means the volume will be 0. So we don't have a box. So we know y and x cannot equal 0. So therefore, what makes it 0 is this part here. And same thing on the other side. So we have this being true. And so is this. And if we just bring over the x squared, so add x squared and the add y squared, we get that. Now, the reason why I did that is if you notice, they equal the same thing. Well, if x squared equals, let's say 7, right, whatever this ends up being, and y squared also equals 7 because it's the same equation. So we know x squared must equal y squared. Well, in general, x equals y. So it started off really bad, but it ends up pretty nicely, hopefully, right? After, the derivative is the hardest part, most difficult part, but once you set equals 0, things actually break down kind of nicely. Okay, so that we know that, x and y must equal 0. Now we just got to find z. Okay, so if I go back over here, or not x and y equals 0, but x equals y itself. So now we can backtrack a little bit to get what we want. So now if you go back to our portion here, we can find what x and y have to be. So if we go back, if you go back here, you just do this, run out of space here. Maybe write this one here. Yeah. And I can use this one, but I'll use this one. And I'm going to plug in everywhere I see y to be x, because that's the same process. Get that. Yeah. And now I just want to solve for x. So add this over, and then divide, we get x equaling 2. Now I know it's plus or minus 2, but minus doesn't make sense, right? So we just get the positive instead because it's the real world applications. So therefore, since x equals 2, this also equals y. And now we can go way back here and solve what z is going to be. So 12 minus 4 is 8. 8 divided by 8 gives you 1. So z must equal 1. So our volume is going to be 2 times 1, or just 4, when x equals 2, y equals 2, and z equals 1. There we go. So don't worry, we're actually going to revisit this question in a little bit as well. Okay. So the last part of this section is absolute min and absolute max values. Okay. Now we talked about this a little bit last time. However, we're going to talk about it something in a closed interval. Okay, so that's what makes it even more not rigorous, just tedious itself when it's on a closed interval. So back in the day, a closed interval meant this, right? We just include the endpoints. And whenever we want to find the minimum and maximum values, we had to include those endpoints, right? So we had to say, okay, we're not just everything on the inside, but include the A's and B itself on the outside. Same thing applies in multivariable calculus, okay? Now, when it comes to closed sets, in our case, a closed set will be literally has sides. So things like this. So not including the boundaries. So like that. So in other words, it has to be strictly less than or equal to, because it includes the boundaries. These are strictly less than or greater than. Okay. So because of that closed set, we have a very special theorem. So the extreme value theorem. So if f is continuous on a closed bounded set in R2, then f has an absolute min values at x1 and y1, and absolute min values at x2, y2 at the points, x1, y2, and x2, y2, if the steps are done. So these are the 3 steps we have to do. So first, find the values of f and make the critical point. So just like we've done so far, find the critical values. That wasn't too bad. Next, however, is find the extreme values of f on the boundary. That's what makes it a little tedious. And then the last one is the largest values is the absolute max, and the smallest values are the absolute min, which makes sense, right? So biggest number is the maximum, smallest number is going to be the minimum itself, right? Now, the reason why I say this is kind of tedious is because we have to check every boundary point itself. Okay. All right. So first off, let's figure what's going on here. So we have a function, but we're given its boundary to be a rectangle. X goes from 0 to 3, and y goes from 0 to 2. So this is our closed set right here, this rectangle. So this has boundary points of 0, 0, 3, 0, 3, 2, and 0, 2. Okay. and that's going to be important in a little bit. All right, but first, let's do what we know how to do. So find mins maxes, we take the partial derivatives with respect to x and y individually of our function. So taking the derivative of respect to x, 2x here, and negative 4y, and that's it. Okay. This one gives us negative 4x plus 2. Right, set n equal to 0. We get that. However, on this side, we can solve for x. X equals 1/2 here. And if I plug that into there, that divided over, so y equals 1/4. So my critical value, or a critical point for now, is 1/2, 1/4. Okay. So now if I plug that in to my f, right, so plug in 1/2 and 1/4 respectively, I get out approximately 1.25, or yeah, let me put 1 because I put everything in decimals there, and we're going to keep that there. Okay, so that's our only critical value. So we don't know if it's a min or max, but we know it's a critical value. Okay, now this is why I say this is going to be tedious when it comes to boundary points. Now we have to check all boundary points. Okay, so all four can actually double it, because what this works out because of boundaries is because this is going to be side 1, side 2, side 3, and then side 4. Okay, so that means for side 1, we have y equaling 0 all the time, and our two boundary points are 0, 0, and 3, 0. Okay, so now our function f of x, y, means if I plug in 0 in for y, I just get x squared. So now I'm going to plug these 2 points in to x squared and see if it's the min and the maximum. So if I plug in 0, 0, we get out 0. So that's the min between those two. Okay, and if I plug in 3, 0, we get out 9. So that's going to be the maximum there. Okay, now we have to do this for all 4 sides. And then from there, we get to pick which one's going to be the largest and which one's going to be the smallest. Okay, so now we go to side 2. So side 2 represents when x is always strictly going to be 3, right? It goes from 3 to 3. So x is strictly 3, and y is what's changing. So if I plug that into x, y, so plug in 3 everywhere, we get 9 minus 12y plus 2y, because y is going to be changing. Okay, so now at the point here, so if I put the point 3, 0, so plug in 0 in for y, we just get 9. And if I plug in the point 3, 2, so then I plug in 2 in for y and just end the subtractions. So I get negative 11. So this is going to be our max. This is going to be our min on this side. All right, 2 more times. So side 3. So this is when y is always strictly 2. So when y equals 2, so plug in 2 wherever we see y. You get that. And then we do the same thing. So again, plugging each point, going across. So 3, 2, so f of 3, 2. So now plug in 3 everywhere. So we get 9 minus 24 plus 4. And what do I get here? Let's see, that's 9 minus 24 plus 4. So negative 11. No. Yeah, negative 11. I think that's 11. You guys can tell me in the comment, in the chat if that's incorrect. I think that's right. And then we do 0, 2. Oh, y is 2. So the other way, yeah. Okay, 11, okay. So now plug in 0 everywhere for x, and that just gives me 4. So this is our max. This is my min. Okay, one more time. Side 4. Now it's this one here. So side 4 means what's being constant. So x is always 0. F of x, y equals, so if x is 0, we just get 2y. That's much easier to deal with. So plug in 0, 0. We get 0, so it's probably going to be our minimum. And then plug in 0, 2. So that gives you 4. Yeah, so this is a min, max. Okay. Now we compare. That's all we're going to do is compare. So we're just going to make the easiest one. Let's go to maximums. So we have 9 max, 4, 4. And we don't know if that's a min or max, right? We just pick it. Okay. So out of all of them, 9's the biggest, right? So that's our absolute max. So absolute max occurs at the points 3, 0, and where's the other one? Oh, just 3, 0. Because they're both the same. Right, cool. So 3, 0. All right, absolute min. So 0, so negative 11, there's nothing. So that's not even a min or max, right? So it could be a local min, local max. So absolute mins happen at negative 11. So what? I want to put this right. So equals 9. So these happen at the points 3, 2, and also same 3, 2. So this is equal to negative 11. There we go. So like I said, it's not hard, it's just tedious because you have to check all the boundary points. So when it comes to closed intervals or closed sets, it's just tedious work. You know, it's not hard, I don't think, but it's just tedious work. Any questions there?